Welcome back. In this class, we are going to review the concepts that we learned in the chapter on charge flux. We said there's a huge need to look at the charge flux aspects, which are typically not looked at by many different engineering disciplines, except maybe for electrical engineers. Not many people look at charge flux. We biological engineers need to look at it because our fundamental biomolecules, out of which all biology is made of, such as lipids, carbohydrates, proteins, and nucleic acids, these four fundamental biomolecules. And these lipids are always charged, by carbohydrates, many are charged, proteins charged, of course, nucleic acids charged. And therefore, we need to look at charges. We need to understand charges if we need to manipulate biological systems. Also, charges and their dynamics are responsible for our ability to even sense the environment. Okay? Our brain, our nerves, and so on and so forth are based on the distribution of charges and their dynamics, right? And that we're going to start seeing in the next chapter. Charge is a fundamental physical quantity that is conserved, and that's our interest. It gives us something and a very valuable tool that we can manipulate, because the left hand side equals the right hand side. So the some fundamental visualizations: the space between interacting charges can be considered to be influenced by the charges themselves. This is how Faraday saw it, others during that time also, and that led to the development of the electromagnetism along those lines of thinking, those lines of visualization. The space between the interacting charges can be considered to be influenced by the charges, and the forces between charges are transferred from one charge to the other through the space in which they are located. Therefore, electric and magnetic fields exist at a point in space, even in the absence of actual charges at that point. There could be charges present elsewhere, but there could be a magnetic field where the actual charge does not exist because the influence of charge is over this place. In other words, there's an electric field that is created by the charges. That's the region of influence. Okay. And then we looked at or reviewed the some basic aspects: the charge on the effect of charges on effect of fields, electric fields, on a charged particle. First, the force experienced by a charged particle when it is moving in an electromagnetic field is given by Lorenz's force law as F equals Q times E plus V cross mu naught H. We saw the visualization as to how this happens. The electric field density is E, the magnetic field intensity is H. Mu naught H therefore is the magnetic flux density, and mu naught is the permeability of free space. We know the value here. Okay, this is the visualization of that, and how the plane over which the direction in which the forces act. The electrical force acts in the same direction as the electric field. The magnetic force acts in the direction that is perpendicular to the plane containing V and H. And this is the electrical force here, this is the magnetic force here, this is the plane that contains the electrical component and the magnetic component. And this is the resultant force on the charged particle that is moving in an electromagnetic field. So some basic quantities we needed to define, based on which our whole development is going to be. Charge density is nothing but the net charge in a certain small volume divided by that volume, Coulomb per meter cubed. And the charge flux is nothing but a charge density that is moving with a velocity v. It is Coulomb per second per meter squared. Okay, amount Coulomb of charge per time. Okay, that's a rate of charge divided by the area that is perpendicular to the direction of motion. Okay, and that is given by the charge density times the velocity, the same way mass density times the velocity gave mass flux. Then we said we are going to use I dash for the charge flux, because I we have reserved for charge per time, current. Then we derived the charge conservation equation from very simple considerations. and the differential form we directly obtained as dou rho dou t plus del dot I dash equals 0. The various manifestations of charge conservation in terms of the relevant effects, electric and magnetic fields, are given by the Maxwell's equations. And we saw the Maxwell's equations. The first Maxwell's equation addressed the question, how is the electric field related to the source? That is in this fashion, the surface integral of epsilon naught E dot dA equals the volume integral of rho dV. And then the second Maxwell's equation addressed the question, how is the magnetic flux intensity related to its source, the charge flux? It is related in this fashion, and which is also known as the Ampere's integral law. So these separate laws were put together because they were fundamental laws into these four Maxwell's equations. So Maxwell's second equation is a contour integral of H dot ds. ds is the unit vector in the surface contour direction. dA is the unit vector in the surface in the direction perpendicular to the surface, which represents the surface, of course. The contour integral of H dot ds equals the surface integral of I dash dot dA plus d dt of the surface integral of epsilon naught E dot dA. And this is the ds vector along the surface, unit vector. This is the dA unit vector along the normal to the surface, differential vector. Don't call it unit vector, differential vector along the contour and along the surface. And then we interpreted the various aspects. We also said that there's another term called electric flux, okay, which has a different connotation, and we won't use much of this flux in this course. However, note that there could be a source of confusion, such as this. This flux is different from the way we define our flux in this course. Then, how are electric and magnetic field related is given by the next Maxwell's equation, third one. And here you also run into a term called the magnetic flux. Again, this flux is used in a different form than the normal form that we use in this course. Then finally, the fourth Maxwell's equation gives us a comment on the net magnetic flux out of any region. That's equal to 0. The net magnetic flux out of any region enclosed by a surface is 0, and that is what is given by this. So we also derived the integral form of the charge balance equation, charge continuity equation, by considerations, Maxwell's relations, and so on and so forth. So this is the integral form, surface integral I dash dot dA plus d dt of the volume integral rho dV equals 0. Okay. We had derived the differential form earlier, and this is the integral form. Then we looked at some more fundamentals. We first said that the differential forms of Maxwell's equations are more useful usually, and therefore we converted the integral forms of Maxwell's equations into their differential forms. To do that, we used two theorems from mathematics, the Gauss's theorem and the Stokes theorem. The Gauss's theorem gives the equivalence between a surface integral and the volume integral, and the Stokes' theorem gives us the equivalence between a contour integral and the relevant surface integral. So surface integral, if you want to convert it into a volume integral, you need to do a del dot of the integrand, whereas if you want to convert a contour integral into a surface integral, you'll have to do a del cross of the integral. That's essentially what it is. And we applied it to this and got the differential form of the first Maxwell's equation. Then we applied the Stokes theorem to get the differential form of the second Maxwell's equation, this. And then you did an exercise to convert the other two into their differential forms. And this is the list of all the differential forms of the Maxwell's relationship along Maxwell's equations along with the charge conservation equation in differential form, which we ourselves derived right in the beginning of this chapter. Okay. And then we said when a medium is present, the effects of the medium come into the picture. So far, the development was in free space. The permittivity of free space was used, epsilon naught, and the the permeability of free space, mu naught, was used. Okay. Whereas in a biological system, a medium is usually present, and therefore we need to consider the effect of the medium on the Maxwell's equations. Then we saw that the medium brings in effects such as polarization and magnetization. Polarization is because of the dipoles that are present in the molecules comprising the medium. And magnetization is a similar thing that happens in the medium in the presence of a magnetic field. And what we saw was that you could take the same Maxwell's equations, 1, 2, 3, 4, replace the permittivity of free space, epsilon naught, with the medium permittivity, epsilon, and everything is valid. Okay. So that way it is nice. Only thing is that you also had to replace the charge density with the sum of free charges and polarized charges. Okay. That of course had to be done, and along with it you change epsilon naught epsilon. Mu naught actually remains pretty much the same for a medium as that of free space. Therefore, we don't need too much about mu naught. So that is what happens when you consider a medium, which is relevant to us. Then we saw how we could further simplify the Maxwell's equation to get the electro-quasi-state and magneto-quasi-state equations. That involved the concept of pseudo-steady state, the same that we have seen earlier many times. And if you apply the concept of pseudo-steady state to the rates of interaction between the waves and the biological material and the rate of variation in the waves themselves, the rate of variation in the waves, which are described by all these equations, are much slower compared to the rates of interaction of the waves with the particles. And therefore, all those time derivatives can be ignored or neglected, and thereby we could get much simpler equations that we could work with. And those equations were this. Of course, here there is no difference. This is a much simpler equation to work with. This is a much simpler equation to work with. And here it is pretty much the same. Okay. So these are the electro-quasi-state and the magneto-quasi-state approximated equations of Maxwell's equations. Then we looked at the concept of an electric potential, which you knew earlier. We looked at it in the context of an electric field and so on, and developed some useful relationships from Maxwell's first equation, the Poisson equation, and the Laplace equation. And then we looked at a constitutive equation in electrical aspects. The Ohm's law actually turns out to be the constitutive equation, one of the constitutive equations that is very useful in electrical aspects. Constitutive equation, as you recall, is valid for a class of substances, but not universally valid. It depends on the constitution of the material, and therefore it's called a constitutive equation. So our Ohm's law, which is I dash equals Ke times E or minus Ke times delta V, written in terms of the variables that we've been talking about, is nothing but current equals voltage by potential difference by resistance, and that is written in this form for our systems. Then we looked at the application of Maxwell's equations to get some useful relationships, and we saw how things are written when we go about doing that, how field lines are drawn and so on and so forth. We said that a membrane, a lipid bilayer membrane, can be considered as a capacitor because there are charges on both ends that are separated by a dielectric material, which is a classic capacitor. And therefore, we derived the equation for a classic capacitor using Maxwell's equations to illustrate how you could use the fundamental equations to derive useful relationships. And you all know the basic capacitor equation from your high school, which is nothing but C equals A epsilon naught by D. This is the classic capacitor equation, which can directly be applied even to the lipid bilayer membrane. Then we said that even the basis of the equation that forms the bedrock of EEG design is based on Maxwell's equations, or is derived from Maxwell's equations. EEG, we saw what EEG was, and then this was the equation. Without getting into any of the details, we just saw this as just a possible application. You won't be able to do that at this stage. You need a lot more understanding and so on and so forth. That's probably not required at this stage. Whenever you need to get into that, of course, you go and pick up the necessary knowledge, skills, and so on and so forth to get to this level. Okay, and finally, we saw the effects of charges in solution. Okay, solution that contains charges, highly relevant for biological situations. And how to approach this is what we saw. We saw three concepts, right? And those concepts were electron neutrality. Okay, let me go through this once more. Is an important thing which leads to a lot of confusion when people start out. So pay attention closely to each one of these. Oppositely charged ions could be present in a solution. There are strong forces of attraction between the opposite charges. As long as the number of positive charges equals the number of negative charges, due to the strong force of attraction between the opposite charges, the net charge in that system is zero. Okay? And this is the concept of electron neutrality. A consequence of this is something like this. Thus, an electrolytic solution cannot set up an electric field, although it contains charges, because the number of positive charges equals the number of negative charges. The second concept was that of charge relaxation time. If a unit charge or a certain charge density is uniformly added to a conducting solution, how quickly does it dissipate to give you a new equilibrium was what we saw as the charge relaxation time. We calculated the charge relaxation time based on very fundamental principles, that is Ohm's law, as well as our charge balance equation, okay, charge continuity equation. Based on these, we derived an expression for the variation of the charge density with time in a conducting liquid, conducting electrolyte. Then the solution was this, and the typical rho equals rho naught exponential minus t by tau r, where tau r is epsilon by ke, and the charge relaxation time is tau r, which is epsilon by ke. For water, turns out to be 0.7 nanoseconds. Charges can be relaxed very rapidly, and this has major significance whenever we go about designing things using solutions. For example, charge relaxation needs to be considered while designing systems in which biological materials such as cells, biomolecules interact with electrical fields such as in electrophoresis. And the third concept we saw was the Debye length. If you have a charged surface in an electrolytic solution, there is a region close to the charged surface where electron neutrality is not valid in the solution. That is because the charges whose sign is opposite to that of charges in the plate, or this plate of charges here that is kept in the solution, only the opposite charges will be aligned close to this layer of charges, or this plate of charges. And therefore, there is a certain length, there is a certain region over which electron neutrality is not valid. And that region is called the Debye length. And I gave you an expression to calculate Debye length. Okay. There is also something more which I like to mention here regarding all this. The typical Debye length is about 10 angstroms. Okay, very, very small, 10 angstroms. And also it is good to realize that charge carrying biomolecules in a system do not generate an electric field because they are shielded by counter ions. This is called the double layer counter ion cloud. Okay. So let me repeat, charge carrying biomolecules in a system do not generate an electric field because they are shielded by counter ions. Okay, this is important while you think of designing things. However, when an electric field is applied, the double layer counter ion cloud surrounding the charged biomolecule gets disturbed. Then the charged biomolecule experiences the presence of the field and moves in response to it. Okay. Otherwise, it doesn't. That completes the review of the chapter on charge flux. When we begin the next class, we will begin a new chapter, the final chapter of this course, which considers the simultaneous application of multiple driving forces resulting in either one or more fluxes. Okay, that has very many significances. We'll start looking at that from the next class onwards. See you then.